So the purpose of tonight's training is we're going to, following some questions that we've had on the group, I just want to take you through how you would do some testing on some actuator heads to understand if that's what's causing the issue on the heating system that you're looking at. Just as by way of some housekeeping, if you hear some noises in the background, there are some fireworks going off. Our esteemed neighbours are letting off some fireworks. So I'll if you hear anything, that's what it is. I guess that's the sort of perks of being able to do this on a Guy Fawkes night. But I'll dive straight in, and I'll share with you this little video that I recorded earlier and just walk you through it. So you're probably all familiar with our actuator head. So this is the full range. This is everything from a ZA3, which is a 3-wire actuator, right through to our mid-position actuators. So I'm going to start by having a look at the ZA3, which is by far the simplest. So you can see here, it's a 3-wire actuator. So all this actuator is capable of doing is driving open. There's no switching or anything inside. So all it's going to do is it's going to sit on top of a valve body, and it's going to either permit flow or close flow off if it's on a 2-port body, or if it's on the 3-port, it's going to give you a priority system depending on what you wire it to. So what I want to try and do, rather than just talk about the wiring, I actually want to break one of these down and show you what's going on inside. So I'm just going to go through the disassembly here. The single screw at the bottom will allow the actuator to come to bits. And then inside, you can see the big synchron motor at the top there, that big silver device. And there's 2 screws that hold that in, and there's a cord grip, and then the whole assembly should come to pieces. Now, I don't expect you to have to do this. I'm really just showing you this to give you a bit of an insight as to what's inside the valves, to understand where, what the sort of things could be that could go wrong with these, and hopefully help you through the fault finding of your installation. So I'm just going to break this one down and just remove the motor, and I just then want to show you what is actually in the valve itself, or in the actuator, I should say, because typically the valve is the brass bit that it fits on. We're talking about actuators here. So you can see here you've got the main cam arrangement with the springs on. That's what gives you your spring return. So the synchronous motor will only drive in one direction, so it drives the valve from the A to the B position, and then when you de-energize, the springs there pull it back to the A position. So it's sprung closed, and that's why it's fairly critical that you get the direction right on when you're plumbing these. So you want to go in on A and out on B, because what you're doing then is you want the pressure or the flow of the water to be pushing against the valve. If you have it the other way and you have the flow going with the spring, so to speak, you tend to get the valves are quite noisy, and they'll bang, because when you de-energize, not only have you got the spring tension pulling the paddle back onto its seat, but you've also got the pressure that's in the system. So the paddle tends to slam against its seat, and then it bounces, and it just introduces some noise into your system. So if it's noise that you've got going on in your system, then it could be that the valve is piped the wrong way around. Another thing to look at here with those springs is obviously that everything that's keeping the valve in the closed position. If we talk in terms of, say, a zone valve, where we're not just diverting flow, we're actually preventing flow from happening. Everything that's stopping that valve from passing any water is that spring tension. So another thing to look at, if you've got a valve that's passing, it could be that for some reason one of your springs has become detached, and you can see that they just hook on to little plastic lugs there. And obviously, if they were to come off, you'd hear them rattling around inside, and then you'd have to dig in and take the valve down, or take the actuator down to this sort of stage to be able to reattach that. But again, if a valve is passing, it's not necessarily an electrical issue. Things that can cause the valve to pass is proximity to the pump. So if you've got the pump and it's plumbed less than a meter, so there's less than a meter's worth of pipe work going to the valve, then you can find that the valves will pass, because the pump, with the proximity of the pump, is just enough to be able to push the paddle off of the valve seat. So that's something to look at, and also pump speed as well. So it may be that if the pump's set to maximum, obviously you've got more inertia there that will push or tend to try and push the paddle open. So it could be that it's just part of the architecture of the system that's causing you the issue, or it could be that one of your springs, for whatever reason, becomes detached. And obviously, if you take those off, then you've got, or if one comes off, you've got half of the spring tension that's closing the valve. And you can see at the bottom there where all of the cables come in. This being a 3-wire valve, we've got the earth, which just goes to the main chassis of the actuator. We've got our neutral in and our live in, and those are just on terminals, straight through terminals that go to the 2 wires on the synchronous motor. So there's no switching in there. This is the most simplest of our valve actuators. So what you'll end up with if you break a valve right down to its component pieces is this. Just showing you that really for completeness. And now if we look at the wiring diagram for that, you can see we've just got the 3 wires, and all they do is they drive the motor, and you've got the green and yellow, the earth there, because it's a class 1 device, but no switching. So that's unlikely that you're going to get any issues with that. I guess the biggest issue you could get probably is if the motor burns out, then the valve is not going to drive open. But you know, if you're applying 230 volts to the brown and the blue, the motor should drive over, or the valve, the actuator should drive open. So now we'll have a look at the ZA5. This is probably the most common. This is used for all of the sort of S-plan or the twin zone systems. And again, exactly the same platform as the ZA3. I'm not going to show you the full disassembly here, but what I really want to focus in on is when you do get it to bits, you can see there that we've got the micro switch, which is just sat in the back there. There's actually a better view of this when I do the ZA6 in a minute. You get a bit of a better view of how the micro switch works. But along with the brown, blue, and the earth to actually drive the motor, you've also got the switching contacts. And that's the thing to remember with your heating systems, is when you turn your programmer on for central heating or hot water and you turn up your stats, you're not directly driving the boiler on. Remember, all you're doing is you're telling the valve to move to a certain position, either open if it's an S-plan system, or whatever position you're calling for if it's a Y-plan. But there's no direct connection between the controls at the head of the system and the boiler. It's all done through the micro switches in these valves. So you can see there that again the brown, blue, and the earth are just there to drive the valve open and for safety. And then the switching, the orange and the grey that we're used to, that's what goes through the micro switch. So essentially, this is volt free because the switch contacts there have got no bearing on the actual where the power comes in. So you've got the brown and the blue that drive the motor. That's not in any way linked to the switching contacts. So they're separate. So if we move on a little bit, we can have a look at the wiring diagram, and you can see that as we move the cam there, you can see the little cam lobe just pushes on that micro switch. And like I say, when we look at the ZA6, there's some clearer footage of that. It's not overly clear in the ZA5, but that's the main principle. Motor drives the arm over, that hits the micro switch, and whatever you've done with those 2 switching wires, which should be one goes to a permanent live and one goes to the switch live of the boiler, that's what will actually fire your boiler up. So typical issues you could get with this, again, it could be mechanical in so much as the valve doesn't drive open. So you're applying voltage to the motor, and for some reason the motor won't move, either because the motor's dead or maybe something's gone wrong with the mechanism. So that's one side of it. But also it could be that the actual contacts in the switch aren't making, or they're not breaking. So it could be that valve drives all the way over, but the switch doesn't make, in which case boiler doesn't fire up. Or it could be that when you de-energize and the switch should break, so the cam moves off of the little micro switch and it breaks the circuit, boiler should stop. And it could be that it doesn't, in which case the contacts inside could be tacked up. Normally, if that's the case, something's caused it. So if you would say, be working on the system, something's calling for heat, and you happen to short out something at the boiler end or the pump, or if it's an old pump and it's starting to sink more current, that can just tack up the contacts in there, in which case you get the scenario where valve is closed, so it's in the A position, but boiler is still running away. So now for the wiring diagram for this, let me just move me out of the way so you can have the full whack there of the wiring diagram. As you saw before, brown, blue, and the earth are there to drive the motor, and then you've got your orange and grey. The orange is your common, and the grey would be your normally open output. We tend to wire them conventionally the other way around. So the grey goes to the permanent live and the orange is our switch live out. But I'll show you why that's the case, that we do it that way when we have a look at the 𝘁𝗱𝗱6, the 6-wire valve. But that's quite a clear picture there, and you can see no link between the incoming voltage to drive the motor with respect to the switch contact. So if you wanted to run 24 volts through the switch, you'd put 24 volts to grey, and consequently you would get 24 volts out on orange, having driven the valve over by applying mains to the brown. So that's the theory. Now we'll actually do the test. So the way I'm testing this here is I've got one of these quick test blocks that allow you to quickly connect things up, and then they're perfectly safe. Once you close the cover, there's no exposed terminals. So they're quite a good thing to have in your kit of parts for testing things like that. So you can see that I've just connected up. I haven't energized it yet, but what we're going to do is just a basic continuity test on our multimeter. So first bell out our leads to see what the leads are. So we know that's now 0.2 ohms. And we can see with the valve at rest, so it's in the A position, the motor's not energized, we can see that we've got open circuit between grey and orange. As soon as we close the quick test, you can see the valve starts to progress over. Now, look, thing to note here is you don't get an immediate response. So it's only when the valve is completed more or less 2/3 of its travel that it hits that cam on the micro switch, and that causes the switch to make. And you can see that we're now in the situation where we've got continuity between those two wires, the orange and the grey. And then when we de-energize the valve moves back to A, and you can see that the terminals or the switch springs open, and we've got open circuit. So from a testing point of view, from the 𝘁𝗱𝗱5, that's what you're really looking at. If you're applying voltage, if you're applying mains voltage to the brown, then we should be seeing the motor drive all the way over. And also we should see it complete its full travel. So it should go from A to B and not stop anywhere in the middle. And once it's completed that travel, we should be able to see the change in state of the micro switch inside. So that brings me on to the 𝘁𝗱𝗱6. Now the 𝘁𝗱𝗱6 tends to be the one that you get if you buy the 28mm body. So if you buy a 22mm body, so sort of a 22mm 2-port, you'll get a 𝘁𝗱𝗱5 actuator. If you buy the 28s, you get the 𝘁𝗱𝗱6. Doesn't make any odds other than you've got this extra wire. Now we talked about this in the past, but as well as the orange and grey, you can see you've also got the white wire. So it's quite key that you don't confuse this with the MA1, which is our mid-position actuator, because the MA1 also has a white wire, but the 𝘁𝗱𝗱6 is a 6-wire valve. So just something to be aware of if you're carrying van stock and you need to replace a 𝘁𝗱𝗱5, you can replace it with a 𝘁𝗱𝗱6, but just make sure it is a 𝘁𝗱𝗱6 and not an MA1. And you can't just use the white wire as the indicator, you've got to actually do the wire count. But the principle is here exactly the same as before. Orange is our common, and when the valve is open, the grey, orange and grey are made, and then when the valve is closed, white and orange are made. So the white wire is just the opposite of the grey. So you could use it if you wanted. In some BMS systems, they want to take an output to say if the valve is closed. So you can do that, and you should be able to see from this little bit of video now the actual mechanism, the little cam mechanism. So it's a bit of a close up here. So you can see as the motor drives that arm over, it hits that little white nib there, which is on the micro switch, and that's what causes it to make and break. And now for the wiring diagram. So again, exactly the same as what we've seen before, brown and blue to drive the motor, but now we've got this arrangement with the 3 wires. You can see now the orange is in the center, and then the white is normally closed. So when the valve is at rest, orange and white are connected together. When the valve is energized and it's completed its travel, white disconnects with respect to orange and grey becomes our connection. And I mentioned before, we normally feed in on the grey, we don't feed in on the orange. And that's because if you're using this scenario here, say if you were to replace a 𝘁𝗱𝗱 with a 𝘁𝗱6, if we were to feed the common in on the orange and have the switch out on the grey, it means that the white would go live when the valve is in the closed position, which is fine if it's made safe and it goes into a dead terminal. But if it's not, if it's just left free in free space, you've obviously got a wire that's live there. And again, some people do cut these back. It's not good practice to do that. The best thing is always to terminate it into a dead terminal. But you can see the principle that if we feed onto the grey, so we make grey our 230 volts in, grey never goes anywhere near white. So by doing that, the white wire always stays dead, irrespective of what position we're in. So you can see the switching arrangement. Strictly speaking, orange would be the common, and if it depends what we want to do with it. But conventionally, we feed our common onto our grey so that it doesn't get anywhere near the white from the switching point of view. So I hope that's clear. So again, that's the theory. Now we'll actually do the practice. So I've just wired it up as before, brown, blue, and earth on the mains power, and then again, doing our continuity test, we can see that we've got, if we go with respect to orange and grey, we can see we've got open circuit with the valve in the A position. We go orange to white, we've got continuity. So that sort of proves the wiring diagram that we've just looked at. And if we now energize the valve, so I'm going to energize this, monitoring orange and grey. You can see the valve starts to move over. The switch doesn't make until you get past the halfway point, about 2/3 is what it is. But that little that arm has now hit that cam, and you can see we've got continuity now between orange and grey. That's what we would expect on a normal system. And we can see that now if we do orange to white, that's now gone open circuit, or I mean, it's showing about 10 meg here, but for our purposes, that's open circuit. You're not going to get much current flowing through that. And then as soon as we de-energize the valve, it goes back to the A position. You can see that we now get continuity back again between orange and white. And if we were to do the test with orange and grey, we would see that that's now open circuit. So again, testing we can do for that is, all we're doing is we're belling out the switch, understanding that orange is our common, grey is our normally open, so we would expect that to be open circuit when the valve is in the rest position, not energized, and the white is our normally closed contact. So the last one is really our most complex valve, is the MA1. Again, it's exactly the same platform, so it's exactly the same casing. Everything inside is the same, except for, you can see now we haven't just got a couple of a micro switch in there. We've now got there is a whole PCB in there as well as the micro switches. So there's 2 micro switches plus the PCB, and the reason that's there is because we need it to hold mid position. So we're now not just driving a synchronous motor until it hits a stop. We now need to. The purpose for this circuitry is that if we energize the white wire, it drives to the middle. If we energize both white and grey, it drives all the way over. And then you also get the delatch when you call for hot water. So that's the whole purpose of that circuit board being in there. Same synchronous motor on all of these. And again, I'll just show you how those make and break. So you can see there's actually 2 micro switches there now. We've got the orange one, and we've got the same one that's in the other valves, the zone valves, just in the back there. So you can see it's a bit of more complex device, the MA1. And from a testing point of view, you need to be a bit more careful when we're testing these, because we're not just testing a volt-free switch here. The orange wire will go live when the valve is in the heating only position. So just be mindful of that, and don't just have it, if you're doing this test, don't just have it hanging in midair, because it will go live. Because the voltage that comes out on orange now is tied to what's going on with the rest of the wires on the valve. So you can see here, we've got the white wire which is white, and the blue is what we're actually feeding with mains, and that gets the valve to drive to the mid position. So you can see if we only energize white and blue, now in reality what we're doing there, the white wire is fed from the output from your room stat. So if you just turn your room stat up and you haven't got any of the hot water offs connected, remember with a wide plan system we have to connect the off side of the water, so cylinder satisfied and the hot water off in the programmer. We need to utilize those, and those connect to the grey wire of the valve, because we need that to go live when we're not calling for hot water, because what that will do is it allows the valve to move right over to heating. So you can see here with just white connected, the valve has only traveled to the mid position, and when we measure the orange, you can see we don't get mains voltage out. We only get about 20 volts out. Now most boilers have got a sort of an 80 to 100 volt threshold, so if you're below that on the switch live, the boiler won't fire, and if you're above that, that's when the boiler will kick in. So you can see if you omit the hot water off side, there's not enough voltage coming out of the valve when it's in the mid position to fire the boiler. Now you might say, well, why does that make any sense? Because for the valve to be in the mid position, we would naturally calling for both central heating and hot water. So the central heating is livening up the white, and that's getting the valve to drive to the middle. But the hot water is also being called on, and if you remember, the output from the demand side of the cylinder stat connects to the orange wire of the valve or the switch live of the boiler. So you can see that the voltage that fires the boiler doesn't come from within the valve when you're in the mid position. It comes from the fact that the hot water is calling for heat, and you see this quite a lot. If you're missing, say, hot water off from the programmer, or if you've got a cylinder stat that fails and you don't get the satisfied side, the customer is left without central heating only. They can only have central heating when they're calling for hot water. So it's quite a good one to sort of remember. So what I'm going to do now is I'm going to connect both white and grey to mains. So what I'm recreating here is we're calling for central heating on our room stat, so that livens up the white, and we're not calling for hot water either by the fact that the programmer for hot water is being set to off, or the cylinder stat is up to temperature, so it's now outputting alive on the satisfied side, which would connect to the grey wire of the valve. And you'll see now that the valve will drive to mid position, so the white wire drives the valve to the mid position, and then once it gets there, the grey wire being live carries it over to the heating only. So you can see it's right over at H now. And now when we do the test, you can see we've got mains potential coming out of the orange wire. So that's how we would test an MA1. If you only connect white, don't expect to see mains on the orange. It's going to be somewhere less than 50 volts generally. But with both of those connected, with white and grey connected to mains, valve should travel all the way over to H, and consequently you should get mains out on the orange. Now with an MA1, the thing to remember is that what's holding that valve over to the heating only position, so what holds it right over is the fact that the grey wire is live. So remember, white drives it to the middle. Once it's in the middle, the fact that grey is live, that drives it right over to heating. If you then would say turn your room stat down, you're going to cause the white wire to go dead, which would mean if the valve was in the mid position, it would fall back to water. But because we're still not calling for hot water anywhere, the grey wire is still live. So if all you do is turn your room stat down, the valve will sit over and stay in the heating position. The orange will go dead, so it will stop your boiler. But if you ever find a mid-position valve that appears to be stuck over in the hot water, in the heating only position, it's not necessarily a fault. It just happens to be the last call was for central heating, and when that became satisfied, because water hasn't been called for in the meantime, the valve continues to sit over. they do tend to get a bit warm because you are sinking current through the synchronous motor. So they do sit there and they do appear to be warm, but it's perfectly fine. That's the way they've been designed. So the synchronous motor inside, which we'll see in a minute, is designed to be able to drive to a position and then stall in that position. Now, if you completely de-energize the MA1, so you de-energize both white and grey, you will cause it to fall back to the water position. So this is the synchronous motor that you've probably seen in the top. Now, this is a replaceable part. Everything we've talked about so far, all the switching mechanisms, they're not used as replaceable parts. If that part of the valve fails, then you do need to replace the whole actuator. But certainly the synchronous motors are available, and they're 230 volts, 50 hertz, 5 watts. So, and I'll just show you what they do here. So when you energize them, you get a very slow movement there. So they're quite torquey motors. The gearing inside means they've got quite a lot of torque, because obviously you've got possibly 1.5 bar pressure in the system. So they need to be quite a torquey motor in order to be able to drive the valve to its position. But you see that they only drive in one position. So when you energize them, you just drive them over, and then when they hit the stop, then they're not electrically disconnected. They just sit there sinking current through them. And because it's a synchronous motor, you're not going to burn out the windings or anything. So that's why that's why it's designed, so that you don't have to have all this circuitry to get the valve to reverse. If you de-energize, the springs pull it back. If you energize it, all you're doing is you're sinking current through the motor. If the motor can turn, it will, and it will drive the actuator open. But if it can't, because it's up against the stop, it will sit there, still sinking the 5 watts through it, but not actually turning and not doing it any damage. And the last thing I'll mention is, if you do go to the effort of taking all your valves to bits, make sure you put them back together. Otherwise, you end up with this sort of mess that you need to sort out. So just be a bit methodical as you go through them and lay everything out. Don't just sort of cast it over your shoulder, as I've done here. So that's it for the little video section. If you've got any questions, by all means stick them in the comments now, and I'll answer them straight away. Or if I appreciate there's quite a lot of technical detail here that I'm trying to cram into half an hour, so it may be something you want to go back through and re-watch again and pause at certain places. But I hope you get it. I hope there's enough information there for you to be able to understand what's going on inside the valves, particularly if you've never seen them before. And like I say, you can bench test them. If there's anything wrong with the switching aspect, or if there's anything that goes wrong with the PCB on the mid-position valve, then there's nothing you can do about it. But if it's a motor issue, so you're applying mains voltage across the brown and blue, or the white and blue if it's mid-position, if you're applying voltage and you're not seeing that motor turn, and it's not that it's being jammed up by the rest of the mechanism, it is just that it's, for some reason, it's dead, you can actually replace them. So that's an easy fix. But also remember that all of our actuators are pop top, so you can press the button in and remove them. So if you do need to go to the effort of replacing the whole actuator, you're not having to drain down. All you're doing is you're doing like for like wiring for the one that came out. But what I really want to get across here is the difference between the different actuators, because they all fit on the same body. So I want to make sure that you don't, just because they fit doesn't mean it's the right actuator for the application. But also, if you do need to test them, or you do want to bring one away, you can actually test it and see what's going on with it.